Well, thank you very much for the introduction, and thank you for inviting me. It's a pleasure to come and talk to you. So yes, at Facebook I work on the anti-abuse infrastructure. I'm going to tell you a little bit about that later in the talk, but first of all I'm going to talk about some of the tools that we've built along the way to make our lives, and hopefully your lives, easier. So let's talk about I/O, so input-output. This is where the nice pure world of computing meets the real world, and things get messy. Things get hard and difficult. But we have to deal with this somehow, because this is how computers actually do things rather than just get hot. So why is I/O such a pain? Well, first of all, it's slow. It tends to be much slower than doing pure computation. So we have to put some effort into parallelizing it, batching it, overlapping it, that sort of thing. It's non-deterministic, so the second time you do an I/O, it might not give you the same result as the first time you did an I/O. And that leads to all sorts of problems. So it's hard to reproduce things that happened in production and went wrong, because when you reproduce the I/O, it might not do the same thing. The data may have changed, or the real world has somehow changed in the process. And it's hard to test things, because you want to test things reproducibly, and yet your I/O depends on the state of the real world. So then it's hard to debug it when it goes wrong, and we've got all of these problems that make I/O really difficult. So just some examples of the kind of things that I'm talking about. When you're writing a web server or a web application, you probably have to fetch data from some back-end services, some databases, some other services on your network, caching services, whatever. And these are slow, so you probably have to overlap them. You probably want to batch them to make your web application run fast enough. We often have to write scripts, and these scripts sometimes have to pull data from external services, or they may have to read data from the file system. They may have to do I/O in different kinds of ways. So then, we very often don't bother testing these things or trying to apply parallelism, because it's a lot of effort to go to. And we just think, oh, let's just write it and hope it works. Another good example is build systems. So build systems have this nice property that they build a dependency graph, and then you can execute multiple nodes in the graph in parallel if they don't depend on each other. So that's another example where we want to do I/O, and there's parallelism available. And in this case, the I/O is the build commands that we're executing. So then one more example is a monitoring system, where we've got some kind of system that goes and interrogates all of your production systems and tries to collect data and then gives you information about what's going on in production. So again, that's another example of I/O. So all of these things are kind of hard to optimize, hard to test. And I just wanted to note that I'm talking more here about non-interactive systems rather than interactive systems. Interactive systems have a whole different set of problems and different solutions. So here I'm really talking about non-interactive things. So let's go back to talking about parallelizing I/O. So one of the kinds of I/O that you might do is a query to a database. And if you're doing lots of queries of the same kind to the same database, then you'd probably be able to look at this and go, oh, I can do that much more simply. I can just do a single select query to my database and fetch all of the data at the same time with one query. And that's much more efficient than doing all of these separate queries. And if you wouldn't just write this, obviously. You'd probably write this. But then when things get more complicated, when you've got different parts of the code doing similar select queries to the same database, then actually doing this batching might get really hard. So that's one manual way you might try and overlap or batch things. And if you turn this into an API, you might end up writing an API like this. So this is probably the first time I've shown some Haxl code. How many people know Haxl? Woo, a lot more than I was expecting. Great. OK, so for those of you who don't know Haxl, this is what we call a type signature. So this is saying if this function called multi-get-user has this type, and I'm going to give all of the types in this talk in blue, like that. So the type of this function is something that takes a list of IDs, and it does some I/O, and then it returns a list of user info. So you might invent an API like this that does this batch select query like this. But then you have to remember to use it, right? So if you forget about it and you go and do individual queries, you're not getting any benefit from the batched query. And then, as I mentioned, if you need to batch queries from different parts of the code, it gets really hard because you have to start restructuring things so that you can use this API. So I've called it anti-modular because it means destroying the natural structure of your code in order to apply something that improves performance. And of course, this kind of batching is very specific to the kind of I/O that you're doing. You can only do it for this particular select query, for this particular schema even on that database. And if you were batching something else, say HTTP request, you would apply a completely different mechanism. You'd do pipelining or threading or whatever. So other ways that we might parallelize I/O. What about threads? That's an obvious idea, right? The trouble with threads is threads are kind of overkill for this problem. Because threads are really good when you're doing interaction with multiple things, right? You can have multiple threads, and they each have straight line code that embody the interaction that you're trying to program. But if all you're trying to do is just overlap some I/O, then threads are just far more power than you really need. And of course, there's no good story in the threading world for how to do batching, how to combine multiple queries into a single batched query. So threads are too heavyweight. So in many languages, we have these asynchronous APIs that have sprung up recently. In Python, we've got async await, and then JavaScript obviously has asynchronous APIs. There are things in .NET, Hack, which is the dialect of PHP we use at Facebook. Most systems have some kind of asynchronous API. And the idea here is that it's much more lightweight than doing threads. So you have single-threaded computation with an event loop that waits for all of the I/O that you're currently waiting for, and then can continue the computation when any of the I/O returns. So it's like a sort of lightweight way of doing threads. In some of these systems, JavaScript in particular, the way you write this is by writing callbacks, which just completely destroys the structure of the program, and it's really hard to program with. In some of the other systems, it's just straight line code, and that's much nicer. But it still suffers from some problems. You still have to remember to use it. Okay, so you've got to remember to make your I/O asynchronous rather than just doing it synchronously. You can get it wrong in the sense that your program will still work, but it might have less parallelism. It might run less quickly than it could do. And you don't get to find that out other than by using some tools or profiling or whatever. You can await too early. You can not parallelize enough things at the same time. And then even if you get it right the first time, later on somebody comes along and refactors your code and they break it. And they don't break it in the sense that it doesn't work anymore. They break it in the sense that it's not fast anymore. And then because your code has this extra structure, it's now got asyncs and awaits and things like that, refactoring itself is harder than it could be. So there is a better way that I'm going to tell you about in this talk. But first of all, I mentioned some other problems with I/O. What about testing our I/O code? How do we do that? Well, we eyeball it and we go, sure, that looks right. We try it a couple of times and it seems to do the right thing. Yeah, that's fine. Well, we can do better than that, actually. If you're really serious about testing your I/O code, you can do things like writing a mock API for the I/O that you're doing. And a mock API is an API that looks exactly like the I/O API that you're using, but it doesn't really do I/O. It just simulates the I/O. So in order to do that, you have to have some test data. So your simulated database has to have some test data that it's populated with. And you have to get that from somewhere, and that might be hard. Writing the mock is manually is hard and error prone. You might not simulate the API correctly. So writing the test data is hard and error prone as well. But building these mock abstractions in such a way, because writing the test data is hard, you probably want to record real test data. So you build an abstraction that can actually record the real test data and then replay it inside your mock. But that's hard work to implement that. And then you have to do it once for each different kind of I/O that you want to mock. So we can do it. We can test our I/O code, but it's really hard to do that. So often we just don't bother. What about debugging? What happens when something goes wrong in production? So you've got an instance of your web application. It gives some strange error in production. You want to try and debug the error. But the data has moved on, the data has changed, and you can't reproduce exactly the problem that you had in production. So that's really hard. One thing you can do is logging. So you can just print out lots and lots of stuff, and you can save it to some log file. And then you can use that to try and diagnose, without being able to reproduce the problem, try and diagnose exactly what happened and fix it. So let me take a little digression into the world of what I call big hammers. So a big hammer is when you use a technology or a library or some kind of abstraction that really takes a hard problem and solves it once and for all, makes the problem just go away, sometimes multiple problems. Okay, and these big hammers might be non-trivial to adopt, so they might require a fair bit of effort on your part. Maybe you have to write some boilerplate, or maybe you have to change your workflows or whatever in order to use the big hammer. But then once you've gone to the effort of applying this big hammer, it pays for itself over and over again, and you end up being really glad that you did it. So let me give some examples of the kind of big hammers that I'm talking about. One is distributed source control. So we all take this really for granted these days. Everybody uses distributed source control, but it was unheard of 20 years ago, right? And it's completely revolutionized the way that we do collaborative software development, because it means that, you know, on a plane you can commit changes, and then you can share your changes when the plane lands with the people you're working with. But it requires effort. You know, you've got to go to the effort of creating a repository. You've got to go to the effort of committing changes and writing change logs and all this sort of stuff. But we recognize that there's a lot of value to doing this, so we use it. Garbage collection is another really good example. So garbage collection in languages that have it just makes the problem of memory management completely go away. You just don't worry about it. Well, okay, there's maybe an asterisk there. You maybe worry about it when it comes to optimizing the program, but it helps a lot at the programming level. Anybody that does a lot of C++ knows that memory management is really hard. So garbage collection solves that problem. One that I'm pretty familiar with, I'm not sure how many of you will be, but the idea that you can have language-independent remote procedure calls. This is where you can talk to any other system on your network, in your collection of systems, using a single protocol, using a single definition of the types and the calls and results of that service. And the idea is that with a single specification, you can, in any language, talk to any service on the network. And this is just a game changer for any heterogeneous system, any system comprised of multiple different components written in multiple different languages. Just makes the whole thing much easier. So at Facebook, we use, I think, a thing called Thrift, which is owned by Apache. There are other such things like Google protocol buffers, for example. So another example that's maybe not quite so popular these days, but network transparent UI. So this used to be very popular, and the idea is that you run a graphical desktop on your local system, and then you can run programs that display on your desktop anywhere on the network, on some other machine on the network, and they just behave exactly as if they were running locally. So this was a really nice idea, but it kind of got destroyed by 3D rendering and things like that. So that was a nice one. Final one, architecture-independent bytecode and JIT compilation, so Java, in other words. The idea that you can write a program and pretty much run it anywhere that there is a Java implementation without changing the code. And you just compile it once. You don't have to recompile or distribute different binaries or do very much in the way of architecture-dependent stuff. So I want to tell you about my big hammer. So my big hammer doesn't have a very catchy name, unfortunately. It just about fits on this long handle. So my big hammer is called Haxl ApplicativeDo. And what these components are, Haxl is a Haskell library that we built at Facebook. We open sourced it in 2014. You can go find it at this GitHub URL. It's been in constant production use since 2015. We built it for a project that I'm going to tell you a bit about at the end of the talk. But we're using this library, exactly the version that's open sourced. You can go look at it. And we're using that in production at a pretty large scale as well, thousands of machines. And to go with Haxl is a compiler extension that we've called ApplicativeDo. And we built this at Facebook again, and we upstreamed it into the GHC compiler. So it was released in GHC 8.0, which is the current major release. And that was released last year. So what these things do is they give you the power to overlap and batch I/O when possible, invisibly and completely automatically, right? So you don't have to do anything in the way of explicit parallelism or batching. Another thing they do is they cache I/O. So every I/O that you do is going to be cached somewhere, and the cache gives you a way of doing record and replay, which lets you do that kind of mock testing that I was talking about earlier on. So it means all your I/O is testable, it's all parallel, and we can also solve problems that occur in production by taking that cached data and using that as a way to reproduce the problem that occurred. So it's a big hammer that solves many of those problems that we have with I/O. On the other hand, it does require a bit of effort to adopt. So you have to write some boilerplate for each kind of I/O that you want to use. But you only have to do it once. So for every kind of I/O, you can write some boilerplate, and then you can share it with anybody else that wants to do that kind of I/O. And when you've bought in, you get parallelism, testability, and debuggability in return. So one other thing I just wanted to mention is that we also added a nice exception framework to the Haxl library, because the other annoying thing about I/O is that you get failure. And there are different kinds of failures, like failures that might happen or might not happen if you tried it again, or failures that will definitely happen if you tried it again because you're using an API wrong. So our exception framework does things like classifies errors into different kinds of failure. So let me do some examples. A simple scripting problem. So let's imagine you've got a set of machines and you've got some software package installed on those machines, and you want to update the software package. And some of the machines may already have the new version, and some of them don't. So what we have to do is, firstly, figure out which versions of the software we have available. Secondly, figure out what machines we have available that might need updating. And then ask each machine which version it currently has, so we can figure out which machines need updating. And then finally, run the update on all those machines that need updating. So let's imagine we have a little API for doing this. So these are our I/O operations. So first of all, get latest version is going to, well, this is its type here. Haxl is kind of the annotation for every function that does something in Haxl, so don't worry too much about that for now. This is like a function that just returns one thing. It returns a version. So in C++, this would be a function of no arguments that just returns a version. Then we've got get hosts, which again is a function of no arguments, and it returns a list of hosts on the network. Next, we can query a host. So this is a function that takes a host as an argument and returns the version of the software that's installed on that host. And then we have an action that we can apply to two arguments. It takes a version and a host, and it updates the software on that host to that version. Okay? And here's the code. Here's the whole code for our little script, assuming this API. So first of all, this is what we call a do expression, and it has a list of statements. And you can imagine these statements just being executed top to bottom. So each of these statements, the right-hand side is the function to call or the expression to run. And the left-hand side is what we're going to bind it to. So this is like saying latest equals, call this function. So first of all, we call get latest version to get the latest. Then we call get hosts to get our list of hosts. Sorry, the code is low. And the third line, I'm calling get installed version, but I want to call it on every host that I got from this list of hosts up here. So this function mapm is something that applies a function, in this case, get installed version, to every element of a list and gives me back a list of results. So then I want to do a little calculation to find out which of those hosts has an old version. So I'm going to look through, I'm going to zip this list of hosts with the list of installed versions, and for every host and version where V is too old, I'm going to collect the host, and this gives me a list of hosts that need updating. And then finally, I'm going to map my update operation over those list of updates to apply. Okay, make sense? So this is just the obvious code that you would like to write. And, well, obviously we could do some of these things in parallel. What things could we do in parallel? Well, the get hosts operation had no dependencies on the get latest version. We can do both of those things at the same time. But then once we've done get hosts, we can do get installed version on all of the hosts at the same time. So all of these can happen in parallel. And then finally, when we've got the results of this operation here and this operation here, we can finally do the updates. But we can do all the updates in parallel as well. So the nice thing is that if you write this code just like it is here, and you run it with Haxl and the ApplicativeDo compiler extension, this is exactly what happens. It just manages to parallelize things exactly as you might hope. So what happened? Well, the data dependencies in the code, and the data dependencies are expressed by the variable names that we're using, that determines the parallelism that's available. Right, so you can imagine breaking up the code and drawing the dependency graph using the variable names. That gives you the parallelism that's available. And the programmer doesn't have to do anything to specify that. They just write the code. And the dependencies that are manifest in the code determine the parallelism. So you don't have to write any explicit concurrency constructs. You just write the code that you wanted, and you get parallelism for no extra effort. But one downside, perhaps, is that you could only do I/O via the Haxl APIs that we've given you. You can't do just any old arbitrary I/O. You have to wrap it in a way that makes it available to Haxl. But in Haskell, because this is a nice typed API, the type system enforces the fact that you can't do arbitrary I/O. It prevents you from doing that. So you can't accidentally go wrong. And I'll show you a bit more about that later. So, of course, when the concurrency is just implicit in the code, you can't get it wrong by mistake. The compiler is going to figure out what parallelism is available and exploit it. I've said it doesn't break when you refactor. Actually, it is possible to introduce false dependencies. If you accidentally plug a variable through into a place where you didn't really need it, you might create a dependency that you didn't really need. And that can prevent parallelism. But that's something you can fix. That's not terrible. It doesn't obviously clutter the logic of the code. So you just get to write the code that you wanted. Another example, let's talk about writing a web page, a blog engine. So web pages are often divided into panes. There are different boxes on the page. And maybe the different boxes are even implemented by different teams at your company. So they're completely different, or perhaps even different repositories, right? So you really like the code for these panes to be modular and not interact too tightly with each other. At the same time, when we execute this stuff, we'd like to be able to execute the code in parallel, do all of the database fetches, whatever, at the same time as we render the panes. So here's a code for a simple page with 3 panes in it. I'm going to have a main pane, a left pane, and a right pane. And this sequence operator in Haskell is the thing that executes a list of operations and returns you a list of results. So then when I've got the HTML for the panes, I can render that and I can give you HTML for the page. All right? We need a little API for talking about the data in our blog. So let's imagine we have a set of posts. Each of the posts has an ID. So we can get all of the IDs for all the posts that are available. For each post ID, we can call getPostInfo, and we can get some metadata about that post. We can also get some content for a post. So given a post ID, it returns the content for the post. Let's imagine the metadata and the content are probably stored in different places, maybe because of scaling issues. And then we can also get the number of views of a post, if we're perhaps ordering posts by popularity, for example. So these all would probably map to SQL queries in some database. So one thing we can do is we can get all of the metadata for all the posts by first of all calling getPostIDs to get all the IDs, and then we can call getPostInfo on each of those IDs, and that returns a list of post info. Let me just show you quickly some code for one of the panes. I'm not going to go into all of the details, but the main pane is going to show the top 5 most recent posts in the blog. Okay? So first of all, I'm going to get the metadata for all the posts. I'm going to sort those posts by date and then take the 5 most recent ones. Then I'm going to get the content for each of those 5 most recent posts. And finally, I'm going to render those posts to produce some HTML. Okay, so again, it's just the obvious code that you would probably write. And when we run this thing, we want to make sure we parallelize all of the code for the different panes. And within each pane, we might have more opportunities for parallelism. So for example, in that main pane that I just showed, we were getting some post IDs, and then we were doing lots of get post infos that could be parallelized. And finally, we were doing lots of get post content that can be parallelized too. So we would like this to just all execute with as much parallelism as is available. Furthermore, many of these queries can actually be batched and combined into a single select query. So as I showed earlier on in the talk, when you have multiple select queries like this from the same database, you can probably combine them into a single batch query. And when you're writing code with, say, multiple panes, even when the code's in different parts of the code base, Haxl will be able to spot these multiple queries happening from different parts of the code and generate this single batched query. Okay, so let's talk about one more example. So the build system is a system that generates a big dependency graph of things that you want to build and executes commands. And when the dependency graph shows that commands can be executed in parallel, we'd like to be able to exploit that and perform those commands in parallel. Okay, let me just show you a quick example of how you might compile something in Haxl. So there's a function called compile file that takes a file path. And in order to compile a file, first of all, we have to figure out what the dependencies of that file are. So get dependencies returns some dependencies. Then we have to compile each of those dependencies, and that returns some code that we got by compiling the dependencies. And finally, we can compile the file that we originally wanted to compile. So this works because we've got a dependency between compiling the dependencies of the current file, and that returns some objects, and the next line here, which compiles the current file. Obviously, you need to have that dependency, otherwise you're going to compile the file and its dependencies at the same time. Okay. So, of course, I've just shown you a snippet of how you might build a build system, but it's not a full build system. It does the parallelism part, but it doesn't do the bit that prevents you from recompiling the same file multiple times. And the other important thing that you need to do in a build system, of course, is remember the dependencies that you needed. And if you come across something that's already been built, you have to check its dependencies to make sure that it's up to date and recompile it if necessary. So you can build all these things on top of what I just showed. But Haxl provides a nice framework for doing the parallelism, and it will also provide a way to do this as well, that we'll see later. So how does it work? Well, I'm not going to go into full details in this talk because they get quite technical, but let me give you an overview of how it fits together. So we want to parallelize things based on data dependencies. Now, the problem with data dependencies is they're not visible to the code. They're not first-class objects that you can talk about in code. So only really the compiler knows about what the data dependencies are. So we need some kind of compiler support to extract those dependencies. But at the same time, we don't really want to build Haxl into the compiler. We want to build some kind of more generic mechanism that lets us do this. So let's look at this example that we had earlier on, where we had 2 statements at the beginning of our script. We were getting the latest version of some software and then getting a set of hosts. These 2 statements are completely independent of each other. But of course, only the compiler knows that, because only the compiler can see the variable names and where they're mentioned. And the compiler normally, when it sees this expression, so this is syntactic sugar in Haskell for this expression down here, and this is what actually gets compiled. So each of these statements turns into an application of this operator that we call bind, which is from the monad class. And bind takes the expression on the left-hand side, and the right-hand side is a function that takes the result of that, of applying that function. So this is what we get to see. And the bind operator has built into it a kind of dependency. So this is its type. And the first argument is a computation. It's abstract. It works in any different monad. And it returns a result of type A. And the dependency that's built in is this result on the left gets passed to the function on the right. Okay, so dependency is built into the way that we execute monads, and there's no way to separate these things from each other. But there's another way to talk about computation in Haskell, and it's called applicative. And applicative has this operator called, I think we call it app, but it has its sort of angle bracket star. And it takes two arguments, and the two arguments are independent of each other. So applicative is the way that you can talk about independent computations and still combine them together. So if we took our example with the two independent statements and we refactored it using the applicative operators, we get something that looks like this. And now the independence between those two expressions is explicit. It's explicit in the code, and we can exploit it in our library. So, just to summarize, we've got these two abstractions. We've got monad, which you can use to express dependent computations, and applicative to express independent computations. But we don't want the user to have to worry about this. The whole idea was that the user can just write the obvious code they want, and they still get the parallelism. So what we can do is we have this pipeline where the user writes the obvious code they want. The compiler looks at the code, figures out the dependency graph, rewrites the code to use applicative where it can, and now the independence is explicit in the code, and we can use that independence in our library to exploit the parallelism. So that's the way it works. The ApplicativeDo extension to the compiler transforms code to use the applicative operations, and then at runtime we're using this library called Haxl, which exploits the applicative operators to give us the parallelism. So just to summarize, we start with this code. At compile time, the compiler generates this stuff. And then in the Haxl library, we're going to implement this operator to give us the parallelism. And it turns out that things can get really complicated. You really don't want to do this yourself, because this is the kind of thing that can happen. If you just write some code like this, we have some variable x1 that's used over here, and x2 is used, well, down there, and x3 is used here. So we've got a bunch of dependencies here. And it turns out that the best way that you can parallelize this is like this. So it turns out we can do A and B in parallel with C and D, and then we can finally do E. But that's not at all obvious from looking at the code. So you wouldn't want to do that transformation yourself. So luckily, the compiler can do that for us. So I'm not going to give you all the details of how the transformation works, but if you want them, you can go read them in this paper. What about the Haxl library? Well, Haxl is a monad. I'm actually running slightly short of time. I might skip through this quite quickly. So the idea of Haxl is that it embodies the essence of computations that can pause and continue later on. And the reason we want to do this is because the computation stops when it needs to do some I/O. And if we can stop in lots of different places at the same time, we can do all of those I/O operations in parallel. So in order to do that, we need a scheduler, or a scheduler. So the scheduler is going to run a computation, and the computation will either return a result, which looks like done A, or it's going to return blocked with a set of I/O requests that it wanted to execute. And then if it returned blocked like that, we just execute all of those I/O requests. And we continue by executing the continuation. So when it's blocked, it returns a continuation that says how to carry on when we've finished doing all the I/O that was needed. So here's an example of what the scheduler looks like. Actually, the scheduler really does look like this. If you imagine that we've got an operation called fetch that takes a list of blocked requests. So this is the list of I/O operations that we can perform at the current time. Then it's just a loop. It says we'll execute the operation. We'll execute the computation. It returns, if it returns done, then we're done. If it returns blocked, then we have to go and fetch the requests that were requested, and then we just go back around in a loop until we're done. So the effect of doing this, let me just skip through this. The effect of doing this is that you get a pattern that looks a bit like this. So we start with an expression. As we run it, it kind of forks into multiple different directions. And then we get a set of operations that we can execute. Those are the yellow blobs. We can do all of these at the same time. So we fetch all of those, or we execute all of those I/O operations at the same time. And then when we finish doing that, we can continue the computation, and then it will maybe come up with another set of I/O operations that we can execute, and so on. That continues until the whole computation is complete. So we call these rounds. We're executing sets of I/O operations in a series of rounds. So the computation is interleaved with the I/O. We do computation, I/O, more computation, more I/O, and so on. So you might be wondering, well, how do I hook up my I/O to this framework? How can I take the I/O that I want to do and plug it into the framework in such a way that I can exploit the parallelism and so on? Well, all you have to do is make a data type for it. So imagine we wanted to do some HTTP requests. We could make a data type. This is a data type for an HTTP request that returns something. And this is the constructor for that data type. And it has a request as its parameter. And when you execute it, it returns some text, the content of the page. So I've made a data type that represents my request, and then I have to make some boilerplate that means the framework can work with values of this data type. So it's kind of like I'm making my I/O explicit. I've made a data structure that represents the I/O, and then it can be manipulated, it can be cached, and we can compare it, and so on. So that's the first thing that you have to do. And the second thing you have to do is make an instance of a class that shows how to fetch multiple instances of this I/O. So you have to define a function called fetch. And when this function is called, it gets passed a list of instances of your I/O that need to be executed. And it's up to the implementation of this fetch function to decide whether it wants to batch them or execute them in parallel in multiple threads, or figure out how best to fetch all of these I/O requests at the same time. But the fact that you're given a list means you can make that choice in an intelligent way. Okay. Yeah, let's just go back to this diagram where we had the series of rounds. What happens if one of these fetches is really big, is much bigger than the other ones? So the problem here is that because we have to wait for each of the fetches to finish, we've got to wait for all of the fetches to finish before we can continue. If one of the fetches is much bigger, then we're wasting time. Right? We could have continued these computations because the results needed for this bit are already available. So that means this is not the optimal way to schedule our I/O. So just interleaving computation and then I/O and then computation is not the best thing we could do. So rounds are too restrictive. And ideally, we should be able to perform some I/O and some computation at the same time and overlap them as much as possible. And then we could kind of make a trade-off between batching and latency. Because if you have a request that's ready to go, you have a choice between whether you say, oh, let's just fetch that immediately, or let's wait and see if there are any other requests of the same type that we might be able to batch together with that one. So it gives you a trade-off that you could make between batching and latency. And maybe if you were particularly latency sensitive, you might say, let's execute things as soon as we have them. Or if you want to optimize throughput, you might say, let's optimize batching. So there's a new version of the Haxl framework with different internals that we've been working on. And it actually does this. So you can execute graphs that look more like this, where you have different sizes of I/O requests and different bits of computation. And they all get overlapped and executed in parallel as much as possible. Okay, so let me just say that we're testing Haxl 2 at the moment. So let's go back and talk about caching. So I mentioned that Haxl caches I/O requests and results. So one nice thing about this is if you execute the same I/O multiple times, you're going to get exactly the same results. And that's, of course, that's really good for performance. But it's good for correctness too, because if you're fetching data from the database in two different parts of the page, it would look a bit strange if when the data changed, sometime during the rendering of the page, you got different results in different parts of the page. So it gives you some kind of correctness, not full correctness, because we don't say anything about what data depends on what other data. But if you make exactly the same request in multiple places, you'll get the same result. And it turns out this is really good for modularity too. What do I mean by modularity? Well, if we didn't have caching, then in order to optimize your data fetching, you're going to have to look at what data is being fetched by different parts of your program. And if you're fetching the same data in different places, you would probably have to common it up somehow. You would have to write some routine that fetches the data and then passes it down to the different components that need it. So it's really annoying to have to do that, because it means that you're coupling unrelated components in your program. You know, you've had to go and look at multiple different components and figure out what data they fetch and make a single component and then pass the data. And maybe later on, when you come to refactor it, you don't know whether the data is still being used or not. You have to go and trace through and find out whether it's still being used. So having to do that is kind of a pain. It's a pain for the structure of your program. The nice thing about caching is it just lets you ignore the problem. So you just do whatever I/O you want to do in different parts of the code. And you don't worry about whether the same I/O is being done by some other part of the code. So let's just take it one step further. So not just I/O, we can also cache arbitrary computations. This is an operation that the Haxl library provides. It's called cached computation. So cached computation takes a key that's supposed to be unique, some computation that you want to perform, and the idea is that if you do the same computation with the same key somewhere else, it just returns the result that happened the first time. So this is what you may know as memoization. And again, the nice thing about memoization is it gives you more modularity than you had before, because rather than having to call a function just once and plumb the results around in your program, you can just call the function from multiple parts of the program. And you can memoize based on arguments. So you can say, if I call the function with the same argument somewhere else, I get the same result. So we at Facebook in particular have found that this has just been tremendous for modularity. People writing code don't need to talk to each other nearly as much if they're using memoization. And that's really good. So as a because people forget to talk to each other, and code bases get large. Okay, so yeah, let's go back to testing. So since we made our I/O into a data structure, we can do things like print that data structure out, and we can serialize it, and we can save it, and that gives us really nice ways to do testing. So at the end of when you've run your request or built your web page or whatever, the cache contains a complete record of all the I/O that you did as a data structure. So if we take that data structure and we save it, then if we reload it again and we run the request, we get exactly the same result, guaranteed. Because the second time you run the request, it's going to do exactly the same I/O requests, and the cache will satisfy them from the results. So we get the same result. So we've built a unit test without having to go to any effort at all. So the way we do this, Haxl provides this operation called dump cache as Haskell. So dump cache as Haskell is an operation that returns a string, and the string is some Haskell code that you can compile, and when you compile it and run it, it populates the cache with all the I/O that you did. So I didn't even have to write any code to deserialize the cache, because the compiler did it for me. So that's really nice. All I had to do was write code to print it out as Haskell code. So in fact, this is exactly what we do to build unit tests for all of our code. We dump the cache, we make a new Haskell module, and then we compile that into our test, and we populate the cache and run the code again. And if the data changes, or your code changes, you just do the same thing again. go and run it against the real data, go and record the data, and save it as a new test. Obviously, you probably want to eyeball the data and the results to make sure they still look sensible, but it just makes it really easy to make tests. So the one kind of overhead here is that we had to make sure that requests are showable, so you have to have some way to print out the requests. But you don't need a way to read it in because you're printing it out as code and the compiler reads it in and compiles it. So let me just say a bit about how we're using Haxl at Facebook, even though I'm running out of time. So we have a system called Sigma, and Sigma is the main engine behind all of the abuse detection that Facebook does. And there's quite a lot of aspects to this. So there's spam, malware, attackers trying to create fake accounts so that they can get spam onto the site, attackers trying to steal other people's credentials and steal their accounts so they can get spam onto the site usually. So Sigma is the main way that we combat all this stuff. And it basically runs a set of rules for various different actions. So when somebody performs an action like they create a new account or they post something or they send a message to somebody, we run a set of rules, and those rules are designed to detect different kinds of abuse. And the rules change all the time because the different kinds of abuse change all the time. And some of these rules are based on machine learning. So we have to collect a bunch of features and we have to feed the features into a model. And that gives us a score to say whether we think it's abusive or not. And some of these rules are just written by hand, manually, to detect some particular characteristic of the attack. And the thing they have in common is that all the logic is written using Haskell, using the Haxl framework that I showed you, and using ApplicativeDo. So we don't really have to tell people how to write parallel data fetching, because most of the time it just happens. So we have a few guidelines to tell people what happens when their code is taking too long to run, how to diagnose it. And sometimes we have things that are too serial when they should be parallel, and we have to tell people how not to serialize things. But by and large, ApplicativeDo just does what it's supposed to do, and it automatically does things in parallel. So we've been running this actually for over 2 years. We think it's probably the largest Haskell deployment in the world. We've got thousands of machines running, all the different data centers that Facebook runs. We serve over 1 million requests per second from this system. And the system is handling abuse detection, kind of integrity activities for multiple different teams and products at Facebook. And internally, we have many dozens of people on these different teams writing Haskell code day to day. In the abuse detection space, you really want to move fast because the attackers move fast and they change things and you have to catch up with them. So we built a system whereby when you make a change to the code base, you can have it running live within a matter of minutes. But of course, we want to make sure that we don't go too fast. It's possible to make mistakes. So we do have a series of mechanisms in place to make sure that we catch errors as much as possible. The one thing I haven't mentioned here is the type system. So the type system is the first line of defense. That catches most of the problems. But then we also have code review. Well, obviously, the type system causes a build failure, so that prevents pushing new code. But we've got automated unit tests using the mechanisms that I described earlier on. We've got automated profiling runs. So when you submit a code change, there's a system that goes away and runs some sample requests against your code change and gives you back a report saying this caused the efficiency of this particular request to degrade by so many % or whatever. So it tells you about performance problems before they get into production. And then finally, if the code gets to go out, then we've got a staged rollout that rolls it out to a certain percentage of machines just to make sure that it's not going to cause any problems before it goes out to the rest of the machines. So we did have to do a few things to improve performance in the compiler. So we made a few tweaks to the garbage collector. One of the things was that instead of having fixed size nursery, so a nursery is the allocation area that you allocate new objects into. We made that into a big pool, so you can just allocate memory from a big pool, and that improved the garbage collection performance. We made various other improvements. Just one final note. So this is not just for big services. So just the other day, I was writing a script, and the script just needed to talk to a few different external services, collect some data from various different places, and write some data back. And if I didn't have Haxl ApplicativeDo, I probably wouldn't have bothered to make it parallel or to make it testable. But it just so happened it was easy to do that. So the script ran 50% faster as a result of just compiling it with Haxl. And I got to do testing. So I just want to advocate this as a nice big hammer for using in your programming. Thank you very much.
So first of all, thank you for the nice talk, Simon. And I've got one key, well, one thing that would interest me is kind of how do you deal with data sources that change over time, and how do you deal with, how long do you cache? How do you deal with cache invalidation? How do you do all of this? Or
yes,
mutable queries where the query actually does cause a change on the other side.
Right, right. So there's two separate questions there, I think. So the question of data changing over time is not something we've really had to deal with in our particular scenario, because most of our requests are fairly short-lived, a matter of less than a second usually. So we assume that it's okay to just build up the cache and then throw it away at the end of the request. We do have some mechanisms to control caching in the library, so you can turn off caching. There are some experimental patches that put a limit on the size of the cache. But the problem is that as soon as you start putting a limit on the size of the cache, it reduces some of the guarantees that you have, so you don't have the guarantee that you get the same result anymore. So we have not put a great deal of effort into thinking about this or implementing solutions to it. But I think there's no fundamental reason why you couldn't implement whatever caching policy you wanted. Okay, the other part of the question was, what about mutable things? Okay, so we have the policy that you can't do a write and a read in the same request. You can't write and then read the results that you got back, because we like to be able to reorder things, and you might do the write after the read and so on. And in fact, the library is kind of built around the assumption that it's okay to reorder things. So if you really do want to have ordering between writes and reads, you have to be quite careful about how you program that. Because, well, in particular, you want to turn off ApplicativeDo because it will reorder things like crazy. So we have looked into that to some extent. So we do have some code, and we have made mistakes where things have been reordered. So the library is kind of taking a stance that it wants to reorder things as much as possible. So writes do necessarily get a bit more difficult in that case. But there's nothing preventing you from having writes. You just have to be careful about how you write the code to get the ordering you want.
Thank you.
So we're running a bit late, so it's a coffee break now. So I think let's stop here. And well, Simon's going to be around for the rest of the day. So if you have questions, you can just come up and ask him. Yeah.